Good morning friends, again here with the chapter Gravitation to continue with. We have seen the gravitational force and acceleration due to gravity. Now next comes about the mass. To define the mass of an object, we know that mass is the amount of matter contained in anything, any substance. Okay, so the particulate matter, whatever the chalk, is comprising of all the small molecules all made of same type of matter. This makes it or defines it as a chalk. So in the universe there is no possibility of emptiness. Everything, everywhere we find that nature tries to fill up or replenish it with something or the other. Some matter, either it may be the three states of matter: solid, liquid or gaseous state. In vacuum, what should I talk about? About the fourth state of matter, plasma, that is also radiated through the vacuum. There is a particulate nature or radioactive elements which are continuously moving through the vacuum also. So somewhere, everywhere in the universe, the amount of matter remains constant. The law of conservation of matter. Matter can neither be created nor be destroyed. Second point, the matter always remains constant in the universe. Okay, this is the proportion that everywhere, if I define this chalk as chalk here on the surface of Earth, it will be a chalk on the surface of Mars even. Okay, so the contained matter, it is not going to change itself, okay, unless and until it is being used or applied force makes any change in that. Okay, effects of force are applicable on each and every object. So unless and until external force is being applied on the matter remains constant, right? Or it can be changed from one form to another form. So that is a part. Here we deal with the property of mass. What is mass? Amount of matter contained in oneself, right? Now this mass is universally the same, as I told just now. It will be constant. Suppose I define mass in the SI unit, that is kilograms. This kilograms is the SI unit for defining mass of an object. Your mass, suppose 60 kilogram. Okay, so 60 kilogram in kgs, I represent the mass of your body. Now this mass, does it have any direction? Your mass in this way, in north is this much, in south is that much, in the east, west or top or bottom somewhere it is different? No. As we know that it has the same value all over the universe, mass will be defined as a scalar quantity, right? Now scalar quantity, mass defined in kilograms. Suppose I say Mahinder is of 60 kilogram, or Mahinder weighs 60 kilogram. Here we introduce the second quantity, that is weight. Okay, I colloquially use the term just I weigh this many kilograms. I'm talking about the weight. Why don't I talk that my mass is this much? Okay, so now again, to understand this weight exactly, what is this weight? Difference between mass and weight we shall see here. Weight is the force of gravitational pull acting on the object. Very simply to tell that the gravitational force exerted by the earth, that is g, small g, this small g is acceleration due to gravity acting on each and every object here equally, uniformly on the surface, you can talk. This and the product of its mass, it is known as weight. The force acting on substance by the gravitational force. So weight will be defined as, weight is given by the product of its mass m into the acceleration due to gravity, that is gravitational pull on it, that is g. Okay, so this mg, which is nothing but the force, okay, force acting on an object. So we observe that weight is given by m into g, so force is directly proportional to this. Which force acting over here? the gravitational force on any object, the acceleration produced due to gravity on any object, that is the force, and that is nothing but what will be defined as weight. So now we know that value of G uniformly suppose being taken as 9.8 on the surface of Earth, but along the heights, along the altitudes, along the depths and on the surface, that is on the poles and on the equators, there is certain difference in this value of G. It is 9.8 and 9.77 suppose at the equator. So accordingly, the weight of a substance may vary from place to place. Clear? So mass, which we saw, was constant in all over the universe. Weight is not the same throughout the universe, right? Next thing, mass being a scalar quantity because it has no direction. Let's talk about weight. Weight is nothing but acting force of gravity, and we know the gravity is center seeking force that is directed towards the center of the earth. Therefore, it has certain direction. Okay, so this direction, perpendicular direction towards the center of the earth on the globe, makes the weight as a vector quantity. So it is a vector quantity in short. SI unit here we saw again, it is nothing but the force mg. Therefore weight will be also given the SI unit, that is newtons. Newton is the SI unit. Again talking about CGS units, CGS unit for mass in grams, CGS units for weight, it will be dyne. Fine with it? So these are the quantities, mass and weight. Okay, certain differences. First, it is constant in the universe, it changes from place to place. Its SI unit is in kilograms, its SI unit is newtons. Secondly, it is the matter contained in any substance. It is the product of the mass with the gravitational pull acting on it, right? So these are the differentiation points between mass and weight. So if I say a person weighing 60 kilograms here, when I measure my weight on the weighing scale, why don't I say my weight is this many newtons? Okay, so what is the difference exactly? Colloquially, we use the common term kilograms. My weight is this many kilograms. Actually, it is the mass what we are telling and not the weight. Tell me, on the weighing scale, what is exactly measured? Here on the weighing scale, I am measuring the mass. Clear? Secondly, think about the balance, tarazu, right? Here both the sides, both the pans are being acted upon with the force of gravity on them. So here it is nothing but the comparison of weights of two different objects in both the balance pans, right? There is a difference in weight and balance, weight and mass. Now suppose mass is 10 kilograms, then what shall be the weight? We are talking about the earth's surface. On the earth's surface, what is the weight of a substance weighing 10 kilograms of mass on the surface of earth? So here calculating in this, weight given as mass of 10 kg into gravitational acceleration constant 9.8, right? That gives us the value 10 into 9.8, that is 98. The unit comes to newtons. This is the weight of the person. So person or matter or object weighing mass 10 kilograms weighs exactly 98 newtons. Okay, so this is the difference between mass and weight. Secondly, for example, suppose an object, now we saw that weight will be different at different altitudes. Suppose example, you are going in lift. Okay, you feel some weightlessness for some instance as you climb the higher floors. You reach the 15th, 17th or 22nd floor, you suffer weightlessness, suppose, or at an instance, suppose you feel lighter in weight. What is that weight exactly now? Here the gravitational acceleration pull along the altitudes being decreasing, you feel somewhat lighter at higher altitudes, suppose in the example of the lift. Same way, the weight of substances will be different on the surface of Earth and on the surface of Mars, suppose. Right? Will the mass of a substance weighing 60 kilograms same on that of Earth and Mars? Tell me. Suppose this is Earth and this is Mars. Okay. The mass of substance weighing 60 kilograms. Okay. Will it be same on Mars and Earth? Yes. Mass remains constant. Although the mass is same, the weight will be different. So, a mass of 60 kilograms on the surface of Earth will weigh how many newtons on the Mars? Okay, so simple again here. By following, the weight is equal to mg. We calculate. We have 60 into 9.8. And that comes to, I think, randomly 6 sets of 48, 4, 9, 54, 54, 58. Am I right approximately? Fine. So just calculate your own calculations. So that is 588 newtons on Mars. Is it same? No. It is 588 newtons on the surface of Earth. Whereas the weight on the surface of Mars will depend upon the value of G on the mass. Are you getting the point difference? Here 60 kilograms is equal to 588 newtons on the surface of Earth with the value of G 9.8. As we saw, the value of G, okay, depends on the mass of the planet, capital M upon R square, right? So that value change in the mass of the surfaces on or the planets where we are landing upon will change accordingly the weight of the person on that planet. Is it very clear? Mass remains constant, whereas weight goes on changing. That can be calculated by using the value of G on that planet. Here we require the G of Mars in that case. So that will depend upon the mass of the planet wherever it is landing upon. So this is the difference between mass and weight. What we saw, 60 kilograms, 588 newtons here on the surface of Earth. The value of G goes on changing at different altitudes and different heights. Thus, the value of weight goes on changing at different locations. We have certain example there as suppose a person is buying 10 grams of gold on the North Pole, Arctic region, right? Now here the weight done by the person is nothing but the gravitational force acting on that object, right? That is G. So it is 10 grams here to understand the mass, but 10 grams makes how much weight? Weight will be different. If the same person checks the mass on the equator, will the mass be same or different? Think, calculate it. Will the weight of the substance measured at North Pole be same as the weight measured at on the equator? Okay, so a person while calculating where are you purchasing exactly and what are you taking exactly, the mass or the weight matters here a lot. Check the example, check this difference with the help of different type of examples. Many examples are there in front of you. So that's all with the mass and weight. Okay, fine with it. Next topic to move upon. Earth's gravitational pull is different at different positions. So now all the objects are under the influence of this gravitational force acceleration. We saw that the feather and also the stone both left from a same height will touch the ground simultaneously. Here we saw the opposite action forces acting on the objects were the buoyant force of the air or the frictional force between the air, which is acting in the opposite direction. But overcoming these two types of forces, unbalanced forces, the gravitational force was much more to overcome these forces. So simultaneously the stone and feather fell down. Suppose in the situation, if vacuum is considered, the same experiment if considered in vacuum, the feather and the stone will truly fall down on the surface at the same time. Okay, this is experimentally being done in the laboratories. So here we define the term as free fall. Okay. What is this free fall? An object under the influence of gravitational force alone will be defined as in free fall, in the state of free fall. What is the state of free fall now? As I told you now, whatever forces, suppose the chalk is dropped down over a certain height to the floor, it will be falling randomly. Unknowingly, we know that the unbalanced forces acting on this object are the frictional force between the air, that is the medium between which it is falling to the earth. Secondly, it is the buoyant force of the air, which is acting in opposite direction to the chalk. Okay, so these unbalanced forces are there to decrease the acceleration to some extent. Acceleration is same for all the objects, whether it may be a large duster or this a light chalk. Acceleration will be constant. We take it uniformly as 9.8 meters per second square. So here, under free fall, we consider a system of isolation with no medium in between the particles. Here, true free fall is possible only in vacuum. Under the condition of vacuum itself, true free fall condition will be there. Okay, so recall again, what is free fall exactly? Now we know that a certain object placed at a height has certain velocity. Okay, it will be initial velocity taking it as u, suppose. The final velocity acquired will be v in that case. Object is dropping down with the influence of this gravitational acceleration small g. Okay, so this initial velocity at the time of dropping will be, of course, 0. Okay, secondly, it will gain, as we saw the example of a ladder or a skid. Okay, so as you go on skidding on the ladder, the acceleration simultaneously goes on increasing. It is maximum just before the time it touched the ground. Fine with it? So this velocity is going on increasing, acting same, 9.8 meters per second square on an average. Right with it? So lowering the heights will go on increasing the value of g, and so the velocity will be certainly increasing in that case. At all such conditions, this acceleration acquired by the gravitational force is constant 9.8 meters per second square. So under the free fall condition, that is where the object is under the influence of gravitational force alone, the kinematical equations for this velocity or the speeds acquired by objects will be given by 3. So just to visualize, do you remember the kinetic equations of velocity? That is, first was, suppose v is equal to u plus at, am I right? Second will be s for the displacement angle. So s is equal to ut plus half at square, and v square is equal to u square plus twice as. Right? So these are the kinetical equations what we studied. Comparison between velocity and time, between displacement and time, and the displacement and the velocity. So these are the kinetic equations. Under the condition of free fall, okay, for any objects. So we'll find these equations as, now here all time the starting position from the at certain height above the Earth's surface is considered to be 0. So to eliminate these values, we get here V is equal to 0. So U is eliminated, gives us AT, whereas the acceleration is the force here produced by the gravitational force. So here A becomes G. Okay, so I represent this as 0 plus GT. Your S is equal to 0, eliminates this T, given by half GT square, and V square is equal to 0 plus twice GS. These are the three kinetical equations to be seen for the condition of object under free fall. Okay, so these conditions are observed in different instances. Suppose the paragliders which move on from high altitude, they drop out of the plane and go on gliding. Here they feel weightlessness, or the weightlessness felt in the space. What is this exactly? I said tell the weightlessness. Okay, you know, the astronomers, you must have seen some videos on the TVs or discoveries that the astronauts suffer weightlessness in the spacecraft, inside the spacecraft. Okay, so therefore that is the reason why pencils are not carried. You know, the Three Idiots dialogues, pencils are not carried, may prick out the eyes. Okay, in that condition all objects go on floating in the spacecraft. Okay, so what is this spacecraft full of this weightlessness due to? Do we consider that there is no gravitational force at that point? Not, of course. We saw there is no such possible condition. There is no gravity acting on objects. If this gravitational force will become 0, then all the solar system, that is the universe, would have been collapsed, not in the same position. Fine. So there is no such thing that there is no gravitational force acting, but it is the condition what we call as the free fall, where the objects or the astronomers and the objects in the spacecraft are only under the influence of gravitational pull. So of course there is the gravitational pull there at that instance is very less, therefore they feel weightlessness. This weightlessness, second example to give you, the Neil Armstrong and videos who have observed on the moon. Okay, so the mass of the moon was 1/6 to that of Earth. Right? Correct. So 1/6. Of course, the mass of the planet decreased, the weight of that object or the person on that planet will be, on that celestial body will be lesser. So here you cannot walk straight on the moon, rather you go on hopping. Why? Because you feel their weightlessness, your weight becomes 1/6 to that of Earth on the moon. Clear? So that is again the example of weightlessness. Weightlessness here defined as only influence of the gravitational pull and no other unbalanced forces acting on that object. That was the example. So your free fall. These are the conditions for free fall. We will be calculating these things. Next thing we'll be talking about the velocities, of the objects if we need to overcome this force. If we would literally want to move upwards, as launching of the rockets, that is the upcoming phenomena, we'll be studying it. For that we need to escape somehow this force acting downwards on us from the earth, by the earth. Okay, so how to overcome that, we'll be understanding it in the escape velocity session. This is all for today. Recall the points, go on pondering your queries, check out each and every phenomena with day-to-day life real experiences. Okay, do correlate your physics concepts with all your physical movements and your phenomena, day-to-day life phenomena in your life. That's all for today. Thank you very much. Let's continue the topic in the new session. Thank you.